So last time while discussing, I think the optical isomers, we were facing some difficulty in understanding the RS nomenclature or RS configuration in Fisher projection. So for that, I have also sent you a video for that, and that's why we have to understand this isomerism basics as well. So let's start doing that, and we'll try to finish this topic today itself. So that's why I won't go in much detail in this chapter, but I'll be doing, or I'll be touching only the main points of this topic. If you find any difficulty in understanding anything, stop me and I'll explain. If it is required, I'll explain it in detail as well. Right. So isomerism, as the name, you must be aware of this. Two compounds or two structures are called isomers if they have same formula, but there is a difference in either physical property or chemical property. So same formula, but different formula means molecular formula, but different physical or chemical properties, or it can be even both, right? That means both physical and chemical properties may be different. This phenomena is called isomerism, right? And the substances which exhibit this phenomena, that is two structures having same formula but different physical or chemical properties, such substances are called isomers, right? Now there are different types of isomerism and isomers. So we divide these isomers into different categories. First division is the main division, that is, it divides into two categories. One is called structural isomers. One type is structural isomer, and the other type is called stereo isomers. So what are structural isomers? A very basic example of structural isomer is, say we have CH3 CH2 OH. So this is an alcohol, and if I want to write its molecular formula, it will be C2H6O, right? There are two carbon, there are 6 hydrogens and 1 oxygen. This is its molecular formula. The same molecular formula can have different structure as well. So what is that possibility? It can be CH3O CH3. Now, even here, the formula is same. There are two carbon, there are 6 hydrogen and 1 oxygen. So the molecular formula is same, but it is clear that first one is an alcohol and second one is a ketone. So obviously, sorry, not ketone, second one is ether. So from this name itself, it is clear that their chemical properties as well as physical properties will be different. One is alcohol and another is ether. So that's why the properties, the main points here are that because their structure is different, so obviously they'll also have different name. They can't have, these two structures won't have same name. So they'll have different name or different attachment or structures. That is structural isomers. Okay, the second category is stereo. That means the name is same, but and even the structure will be same, but there will be different orientation in space, right? So for example, think of this structure. So there are 1, 2, 3, 4 carbon. It is a butene, right? It's a 2-butene. Now, what does it mean? This carbon, the bonds which are not shown here, this carbon here has to have 4 bonds. So the 4 bonds are like this, that 2 bonds are with the adjacent carbon and 1 bond is with this carbon, which is forming CH3. So there is a third bond which is here, that is hydrogen. So it is not shown in the bond line structure, but it is there, right? And this same thing will hold true for this as well. So there will be hydrogen here as well. Now, this is one structure. Another possibility is this. So we still have the same formula, because you can see the structure also is same, right? And there will be hydrogen here and one hydrogen here. Now, what will be the name of these two compounds? It will be same. That is, both the compounds are but2ene. So their name is same. Their mostly their chemical properties will also be same, or properties will be same, or structure is same, right? So if I have to write its molecular form, or its chemical formula, or say formula in condensed form, so even that will be same for both. What will be that? That will be CH3, C, double bond, C, so the same thing will hold true for this as well as this, right? So their structure is same, structure same, molecular formula same, and the thing which we have seen here, this doesn't hold true for this. So here I'll have same name. The IUPAC name of both the compounds will be same. Actually, they are not two different compounds. They are same compound. So their IUPAC name will be same. Right? Now, but their structure is different. Why? Because it is a double bond. So double bond, about this double bond, this rotation is not possible. Right? That means one structure can change to another, or another can change to one. This is not possible. So these two are not two different structures, right? So we say same name plus same structure, right? But different orientation. Right? In space, they have, or in space, they have different orientation. So how to identify that? We can see that this H and this H are on the same side of the, are on the same side, while here they are on the different sides, or diagonally opposite sides. Now this, and why they have different orientation? What is reason for that? In this case, it is possible. Why? Because there is a double bond, and these multiple bonds restricts rotation. So it is not possible for them to change their configuration from one form to another form. So this structures cannot rotate to interchange, and that's why they are also called isomers, but they are a different type of isomers. They are called stereoisomers. So we have now stereoisomers and structural isomers. So structural isomer will be totally different. Even there, as you can see here, they have different name and obviously different structures. But here in stereo, you have different structure, but you have same structure, but different orientation. So that is the major difference between these two categories. Now, The first category itself can be divided into multiple subcategories, which we'll discuss in detail. The first one in this is chain, then there is chain isomers, then positional isomers or positional isomerism, then we have functional, right? And then we have two more types which are little tricky one, that they are called metamers and tautomers. Right. So I think the first three are easy. These are little tricky, that is metamers and tautomers. And coming to this side, that is for stereoisomers. These stereoisomers can be again divided into two categories. This is division for stereoisomers. This is again divided into two subcategories. Here there are 5 subcategories. Here there are 2 subcategories, but 2 are again important. One category is for configurational isomers. Right. So what is here? These are the isomers. As you have seen, there is no difference in structure, only orientation. So configuration falls under that category, so that's why it will also satisfy the same relation. But the thing is, these things can be isolated by general physical or chemical means, right? So this can be isolated by physical or chemical, you can say, methods. That is configurational isomers. Now the one which, so obviously the second category is the one in which this isolation is not possible, and such isomers are called conformational isomers, right? Or conformational isomerism. So obviously these are the one where they cannot be isolated. So this is the difference between conformational and configurational. Configurational can be isolated, and conformational cannot be isolated. This is the basic difference between these two. Now what happens in conformational? So they cannot be isolated first. They don't have any, you can say they don't have any structural difference. They don't have, or they cannot be even isolated. So that's why they are also called not true isomers, right? So they are also called not true isomers. So we are limited to this configurational and the 5 on this side, right? So I think we should finish with this conformational first, because that is very easy to understand. They are basically formed by rotation along single bond. So if there is a single bond and along that there can be rotation, and that can lead to two different you can say structures, then such isomers are called conformational isomers. And the examples for this are, suppose these are 2 carbons, and so this is a carbon, this is a carbon, and then here there can be 3 bonds. These 3 bonds can be like this. This is one configuration. This is called, and as you can see, whatever group is here, same group is here, so there will be a repulsion here. right? So if it is like this, which has more repulsion, this is one of the configurations, or I mean, you can say orientation. Another orientation can be just opposite of this. So the front one can be like this, and the back one can be like this, just opposite of this, right? So here there will be less repulsion, and that's why this will be more stable, right? So stability wise, this is more stable, right? And such forms are also given name. This is called eclipsed conformation, and this one is staggered conformation. So these are two different conformations of same compound. Compound is same. There, if you write their molecular formula, it will be same. You write their IUPAC name, it will be same. But only difference is that there is a single bond here. So about that single bond, rotation is possible. So it can rotate and come to this form. And from that form, it can again change to the first form. So this interchanging is possible. And because this interchanging is possible, they can interchange from one form to another form. We say that it is difficult for us to isolate them. So they are not true isomers. Now, the same thing can also be shown. There is another representation for this, and that is the same thing. To represent this, we use this dot and circle diagram, where circle represents the front carbon and dot represents the back carbon. And the bonds with the front carbon and, sorry, the dot represents the front carbon, and that's here you can draw these bonds like this, right? And in the eclipsed form, the one with the back carbon will be just behind this, but we have to show this. It will be actually totally eclipsed, but we have to show this. So that's why we show it like this. That is just behind the front groups, the groups in the front, right? And staggered will look like this. Right? So these which you see here, they belong to the back. These bonds are attached to the back carbon. And the ones which you see complete lines, they are in the front. Right? And what did we say about this? This is eclipsed, more repulsion, and because of more repulsion, it will be more stable, sorry, less stable, and this one will be more stable. So that is about these conformational isomers or not true isomers. Now let's move to more or important isomers, which are actually true isomers. In configurational, we will have optical isomers, as well as, again, in configurational, again there will be two division. The divisions in configurational are again two. One is geometrical and the second one is optical. Optical was the one which we were discussing in the last class. So these two different isomers are there, optical isomers and geometrical isomers. Optical isomers, the one which we have seen above, sorry, the geometrical, the one which we have seen above. This is actually example of geometrical isomer, this one. This is actually example of geometrical isomer, right? So in geometrical isomers, what we mostly or basically have is there is a restriction due to multiple bond, right? So I'll just write multiple bond induced restrictions are there. So the rotation is not possible. And due to this, there are two possibilities here in geometrical as well. They are the one which the same which we have seen above. One configuration is this, and the other configuration is this. Structure is same, name is same, but orientation is different. So the one which we see above, the above in which these two are on the same side, they are called cis version, and this one is called trans. So these are the two types of isomers, or two types of geometrical isomers, right? And in optical, we have already seen that their behavior towards the plane polarized light is different. So one rotates the, or you can say deviates the, or rotates the PPL, that is plane polarized light, in the left direction, and other rotates in the right direction, right? Or clockwise or anti-clockwise direction. So these are all different types of isomers. Let's see them one by one. Let's start with the structural one. So the first one in the structural is actually chain isomers. So let's see what are chain isomers first. So these are the structural isomers which differ in their main chain or side chain, right? They have different main chain or side chain. So an example for this can be, say, C4H10. So C4H10 is butane. There are 4 carbons and it's a H10, means 4 into 2, that is 8 plus 2. So it is a saturated hydrocarbon. So it can have different main chains. For example, like this, the simplest. This is your C4H10, and it can have different chain length. For example, I can have this. There are 3 carbons here and one more CH3 group attached to this carbon. So what do we have in this? We have one carbon here, a CH3 group here, a CH3 group here, and a CH3 group here. So that means there is one more hydrogen here which is not visible, but it is there. Now this is C4H10 that we know because it is a hydrocarbon and there is no double bond, so that's why it will be C4H10. That is the CnH2n plus 2 formula. Now coming to this second structure, what do we see here? Here it is, the main chain is actually propane. It is no more a butane now, right? And what is its formula? There are 4 carbons, hydrogens, which we are able to see here are 3 into 3 9 plus 1, that is 10. So this is also C4H10, and these two isomers are called chain isomers. The chain length is different. One is of length 4, another is of length 3, right? So what will be its IUPAC name? Its IUPAC name, the second one, IUPAC name will be 2-methyl propane. Name is different. This one is simply butane, right? So you can see the name itself has changed. This is chain isomer. Now there are different ways to find and write all chain isomers of a given chemical molecular formula. We are not going in detail of that. We are directly moving to the next type of isomers. If any one of you need those methods in detail, just let me know. I'll try to make a video on that, or I'll try to make schedule a class for that. right now I want to finish this isomerism chapter so that we can go back to our haloalkanes chapter. So next one is positional isomers. Chain isomers is over. Next is positional isomer. Right. So what do we have here? Here we don't have. First thing is there should not be any difference in the chain. Right. So no difference in main or side chain. That should be exactly same. Then what should be the difference? Difference can be in position as it is positional. So the position of what? The functional group, the multiple bonds or substituents. Functional groups, right? Or multiple bonds or the substituents. They can be different. Now again, functional group should be same, only its position should be different. Multiple bonds should be same. Double bond should not change to triple bond or single bond. The multiple bonds should be same, its position may be different. Or the substituents like chloride or fluoride or nitro or hydroxy, they can be same in two structures, but their position will be different. Right? Examples for this. Yeah, say I have this, right? And here there is an OH attached. So how many carbons are here in this? There is 1, 2, 3, 4, and 5 carbons. So its isomer, its positional isomer can be what? It should have same length, that is 5 carbon. And OH group can be attached somewhere else. Say its position is now changed. So again, what do we have here? We have the same carbon chain structure, the main chain structure, the side chain structure. Only difference is the position of OH. Here the position is 1 and here the position is 2. That is the only difference. So these are the examples. These two are the examples of positional isomers, right? So now, in order to understand whether the two of the things which we have studied, whether we understood or not, just to verify that, let me ask a question to you. Say this is structure 1, then we have this as structure 2, this is structure 2, and this is structure 3. So you have to tell me how many combinations are possible. Say 1 and 2, 1 and 3, and 2 and 3. So now you have to tell me about them, that whether they are positional isomers or they are chain isomers. So 1 and 2. First, even you have to decide whether they are isomers or not. So for that, them to be isomers, their chemical formula should be same. So, or the molecular formula should be same. So first things first, find out their molecular formula. So there is 1, 2, 3, 4, 5 carbon. So C5. Then there are hydrogens. How many hydrogens are there? 3 here, 2 here, 2 here, 0 here, and 3 here. So 3 plus 3 plus 4, that is 10. And there is a oxygen. So you will have to satisfy yourself that all these formulas are same, then only all of them will be isomers. Otherwise, if the formula itself is different, then they may not be isomers. So again, this compound 1, 2, 3, 4, and 5. So total 5. So this is C5. Then hydrogen 3 here, 2, 2, 3, and here 0. So this is C5H10O. The third one, 3 3 hydrogens, 1 hydrogen, 0 hydrogen, 3 hydrogen. So this is also C5H10O. Right. So what we see here is they all have same molecular formula. So because their molecular formula is same, so all of them are isomers. But which type of isomers? So we take combination of two. So first and second, I think I have got some answers. 1 and 2 are position isomers. Okay. 1 and 3 are chain isomers, and 2 and 3 is also chain isomers. Yeah, I think I got answer from Nikita. So 1 and 2 are the only positional isomers. So this one, these two are positional, and these two and these two are chain isomers. So this is very important to understand, and this example was to make sure that we understood the concept of chain isomers and positional isomers. Remember, the first priority is given to chain. If there is difference in chain, then it will be chain isomer. Because if you see second and third, or first and third, right? So in first and third and second and third, chain length is different, right? And in first and third, if you see, position is same, but in second and third, even the position of functional group is different. But still, we don't say that it is chain isomer and positional isomer. I hope you understood. This is chain isomer, not positional isomer. We cannot say that both position is also changed and chain is also changed. So it will be both chain isomer as well as positional isomer. There is a well-defined priority here, that is the chain has higher preference than position. Actually, we are studying in the same order. So we are done with chain and position. Let's try to finish the functional isomer as well, so that the basics of structural isomers will be over today. So the next group is, or the next type is functional isomer. The name, from the name itself, you must have got the functional groups will be different. So here the chain and all is not considered here. The structural isomers which differ in chemical reaction, right? So their main problem is, or the main difference is, that they differ in chemical reaction. And if they differ in chemical reaction, that means what? Their functional group is different. So different functional group. So if that is the case, such isomers will be called functional isomers. Let's see example of that. Actually, the first example which we have seen above in structural isomers, that is an example of functional isomer. So say for example, if I have this structure CH3, CH2, C double bond O, H. So this is an aldehyde. You have 3 carbon, 3 plus 2 plus 1, 6 hydrogen, 3 carbon, 6 hydrogen, and 1 oxygen, right? The other for this can be, other structure for this can be CH3, C double bond O, CH3. Now what do we see here? This one is actually a ketone, and the formula for this is same, that is C3H6O. So the formula is same, but one of them is aldehyde and another is ketone. So the name itself is different. One is aldehyde, other is ketone. The family itself is different. So that's why their reaction will also be different. Such isomers are called functional isomers, right? And now this functional isomer, because in this class, that is 12th class, we'll be studying more of functional groups, different functional groups. So functional isomers become very important topic for us, right? So that's why we'll be studying these functional isomers in more detail, maybe later. Now, whenever two compounds given and relation is to be found, the first we have to find whether they are homologues or not. That is same functional group. Then we go for the second step, that is then we decide whether they are isomers or not. For isomers, their formula should be same. Now, in the isomers, the first preference among the three which we have studied, the first preference will be given to functional group, then second preference will be given to chain, and the third preference will be given to what we have already seen. After chain, it was positional. So in this particular question, you may come up with this doubt that why not positional isomer? So this is the answer for that. These are not positional isomers. Yes, even alcohols and ethers are functional isomers. So as you can see here, aldehyde and ketone, these two, and this you have to remember this part, that they are functional isomers, and functional isomers have higher preference than all others. In fact, they have the highest priority. Functional group will have highest priority. So that's why you can see that this position is 1. Here the position is 2. So this is positional isomer as well. But no, it is not positional isomer. It is actually only functional isomers. Right? So that is about different types of structural isomers, the important structural isomers, the basic, we'll say not important, just the basic functional isomers. In the next class, I think today we are not able to conclude this. So maybe in the next class, we'll try to finish the rest of the isomers, including optical isomers. Optical isomers, I think we have already done. Only that RNS configuration we have to study, right? So that's all for today's class.
Yes, sir.
Okay, next physics will be at 5 p.m.